For as long as we've had clothes, we've done laundry. Long before detergent pods and spin cycles, people figured out the simple trick of rubbing textiles against rough surfaces, which squeezes dirty water out of the fibers and pulls cleaner water back in. Roughly around the 1800s, the idea got a dedicated tool that you still occasionally see today, even if only in jug bands. The washboard spread across the world as a faster, more practical way to scrub shirts and pants. Its use continued to grow until automatic electric machines took over in the early 20th century. But we're not here to talk about laundry. That era wasn't just the heyday of the washboard, it also marked the start of the highway era, at least in the US. When road construction boomed and traffic skyrocketed, including on the unpaved routes that connected farms, towns, and job sites. If you've ever driven on a dirt road, you know one of their biggest problems. In some places, the surface organizes itself into a repeating pattern of ridges and valleys that can rattle your teeth, shake your suspension to pieces, and make the vehicle feel like it's skating. It's obnoxious at low speeds. At higher speeds, it can become legitimately dangerous because bouncing tires can cause you to lose control of steering and braking. In 1924, this phenomenon was known as rhythmic corrugations. By 1929, people were calling them washboard roads. And nearly a century later, there's still a persistent problem all over the world. What's surprising is that this is still an active area of research. In the past decade or so, there's been a burst of papers trying to explain exactly how washboarding forms and how to stop it. I was reading one of those studies when I saw the experimental setup they used. The moment I saw it, I knew I had to build one. Let's talk about why this happens and why there's still more to learn about washboarding. I'm Grady, and this is Practical Engineering. Roughly 35% of the countless thousands of miles of roadways in the United States are unpaved. That's technically true, but a little misleading since most of those roads are in rural areas that carry only a tiny fraction of the traffic volume compared to the roads paved in asphalt or concrete. This is not a measured or reported statistic, but some back-of-the-envelope math shows that only about 1% of traffic happens on unpaved roadways in the US. That's not true in other parts of the world, though. We call that outer layer of a road the wearing surface for obvious reasons. Of course, using a hard material like asphalt or concrete as the wearing surface has a lot of benefits. It cuts down on dust, it's generally smoother and more comfortable to drive on, it's easier and safer to drive at high speeds, and it's more durable. But as good as it is, paving doesn't make sense in every situation. Almost everything in transportation engineering is an economic decision. Roads seem kind of mundane and simple, but you have to consider the scale. Think about a basic home improvement project like installing new flooring in a kitchen. Maybe it'll cost you a few $1,000s. Then consider that a mile or 1.6 kilometers of two-lane roadway has, very roughly, 600 kitchens worth of surface area. For a simple commute to work, we're talking about thousands or even tens of thousands of kitchens now. This is silly, but the point is that roads are extremely expensive, not because they're particularly sophisticated, but because they're huge. You don't get a monthly road bill, but if you add up gas taxes, tolls, and the slice of general taxes that fund roads, the average household in the US is paying roughly on the order of an electric bill each month. So engineering decisions about roadways are largely driven by costs. Here's a simple example. An unpaved road is pretty cheap to build. Before we consider the traffic, it sits pretty low on this graph. But as traffic increases, so do the maintenance costs associated with regrading, adding new gravel that's lost over time, controlling dust through chemical application, etc. Its fixed cost is low, but its variable cost is steep because it's not as durable. A paved road is expensive to build initially, but it requires less maintenance, and that maintenance is less sensitive to traffic volume, so its variable cost is relatively flat. You can see there's a break-even point based on traffic volume, below which it makes more sense not to pave a road. And that's just looking at traffic. when you factor in other complexities like the availability of materials, the abundance of skilled contractors who can do the work, and climate factors, there are plenty of situations where paving a road isn't the best economic decision. In many countries, pavement is a luxury reserved for only the busiest highways. My point in all of this is to show you that washboarding isn't just a problem of the past, it's a real and present challenge, so it makes sense that we're still trying to understand how and why it happens. I mentioned there's a lot of ongoing research into this question. Those papers can be pretty hard to wrap your head around. So I figured I'd build a demonstration so we can see it happen in real time. A lot of these parts came from my friends at Send Cut Send. My local hardware store didn't have a circular sand track and a motorized wheel arm assembly on the shelves, so I had to design this myself. I could have spent days out here fabricating it too, but I'd rather spend that time making more videos for you. Send Cut Send makes this so effortless. They give anyone with a CAD file access to laser cutting, CNC machining, bending, powder coating, and more. They don't have minimum quantities, it's super fast, super easy, made in the USA. They have completely changed my workflow out in the shop, and they support what I'm doing on the channel. This is the easiest recommendation I can make. If you need parts made from metal, acrylic, or any of the other materials they have available, give them a try at the link below. Here's how I set this up. In the center, I have a stepper motor connected to a gearbox. I chose a stepper because the hardware is relatively cheap these days, and with the built-in encoder, I don't need a separate system to keep track of the speed. The power supply and driver for the motor are over here to the side. I'm pretty new to this stepper stuff. This is not related to washboards, but I just think it's cool. This controller sends pulses to the driver, which energizes the coils of the motor in a careful order. The trick is that it also knows whether the motor actually did what it said to do, so it can adjust or throw a fault if something goes wrong. For the 90s kids, it checks itself before it wrecks itself. It took me some time to wrap my head around it, but now I just have a button and a knob to do exactly what I want. This arm is attached to the gearbox and has a wheel assembly on one side and some bolts for counterweight on the other. The wheel runs in a circular track of sand I made from polycarbonate sheets. I use polycarbonate rather than my typical acrylic because it can flex more without breaking. Turns out that not much will stick to it though, so I ended up bolting the pieces together. Now that this is set up, I can just push go and watch what happens. And what happens isn't really too interesting at first. This does just about what you'd expect it to. The wheel digs a rut in the sand as it goes around and around the track. Right now it's moving at about 1 meter per second, or roughly 2 miles an hour. I let this run for an hour with pretty much no change in the behavior. But watch what happens when I ramp up the speed just a bit. And actually listen too, because it's easier to hear than see at first. After only a few laps around the track, you start to hear a rhythm. It doesn't take long at all before the wheel is literally galloping between each bump. I have to be honest, I didn't think it was going to work this well. Let's take a closer look to see what's happening. I'm going to smooth out the sand and start this again. But critically, there's no way for me to make this surface mathematically smooth. There are always going to be some small random bumps and dips. And it turns out that's really important here. My wheel has some freedom to move around this clevis pen so it can go up and down bumps like a regular vehicle would. The wheel's not rigidly being pushed through the material, it's in a conversation with the sand. Because there is some irregularity in the surface, the force between the wheel and the sand is irregular too. When we hit a bump, the force is briefly higher, causing the sand to be plowed forward, and when the wheel encounters a dip, the force is less, so less material is shifted. That fluctuation in forces matters because the wheel starts changing the surface of the track unevenly. As the wheel rolls up off a bump, it unloads. But what goes up must come down. The wheel has inertia, so when it falls, the downward force on the surface is higher than when it's just rolling along. If the speed is fast enough, that impact happens a little after the lowest point, so the sand is pushed and piled downstream of where the wheel hit, creating a new bump where there wasn't one before. One bump becomes 2, becomes 3, and so on. Each pass makes them a little bigger and organizes them a little better until you get that rhythmic corrugation in the surface. Eventually, the bumps are big enough that the wheel follows a ballistic trajectory, literally jumping off the surface with each one and slamming back down on the other side in just the right place to push more sand up the following bump. The only thing limiting the bumps from growing indefinitely is the natural repose of the sand. It can only stand up so steeply before it flows down into the next dip, filling it somewhat. This is why these washboards can travel like sand dunes, slowly moving down the road. Understanding all this, it makes sense why washboards often emerge in transitional areas of a road. Curves, changes in slope, and at connections to paved roads. You need a fluctuation in tire force to get the process started, and these are places where, even without a bump, there's a higher likelihood of a sudden change in force that could start to shift the material. What's interesting is how robust the instability is. You would think that differences in vehicle weights, wheelbases, suspensions, and speeds would tend to smooth things out. It turns out they don't. In fact, you don't even need a wheel to do this. Researchers have shown that even a simple angled plate that acts like a plow will form ripples above a threshold speed as long as it has the freedom to move with the bumps. It all feels a bit counterintuitive. It'd be easy to assume that an angled plate would smooth out the road like icing on a cake. A big part of the reason things don't smooth out is that the washboards are self-perpetuating. They impose a periodic force on the vehicle tires that, in turn, amplifies the forces creating the corrugations. It's like the Tacoma Narrows Bridge, where the wind amplified the torsion, and the torsion amplified the wind's effect on the deck, a positive feedback loop of instability that only gets worse over time. The washboarding of roads is just one example of what scientists call a pattern-forming instability, where structure emerges from a system that starts out more or less uniform. We see them everywhere in nature, from chemical reactions to the markings on animals, and washboarding has some natural analogs. In rivers, moving water transports sediments in a way that can form ripples on the bed. I caught a cool shot of this phenomenon in action for my video about reservoir sedimentation. At a larger scale, river meanders are often described in the same way. Even a straight channel will, under the right conditions, begin to drift sideways as curvature redirects the fastest flow toward the outer bank, strengthening erosion there and deposition on the inside. I have a couple videos on that process too. But the fluid doesn't have to be water. In places without much vegetation, wind-driven sand doesn't naturally smooth out. Instead, it forms dunes that can march across the landscape. In all these cases, the same basic feedback loop is at work. The driving force reshapes the surface, and the reshaped surface redirects the driving force. It's the same thing with washboards. Small bumps change how a wheel loads and shears the gravel, and that shifted, uneven loading moves material in a way that makes the bumps grow into a repeating pattern. Characterizing the factors that play a role in the formation of washboarding helps you make engineering decisions about how to avoid it in the first place. The obvious solution is to use a more durable wearing surface like asphalt, but we've already covered why it's not always the best option. Plus, it's not like asphalt is immune to damage. Speed is the most critical factor for washboarding. Maybe slowing down is a useful suggestion on a personal driveway, but it's not particularly viable as a widespread solution on public roads, especially the low-traffic roads where enforcement of speed limits is less than strict. We want to get where we're going, and we want roads that can safely handle the speed, so most of the focus is actually on the materials used in roadway construction. Typical roads use a base layer below the wearing course. It can get a lot more complicated than this, but in nearly every case, the base material is usually doing the heavy lifting. The material used for road base is broadly graded, meaning it has particles of lots of different sizes, from gravel size all the way down to microscopic clay-sized grains. Often it's made from crushed rock, which naturally produces a good mix of particle sizes. All those different sizes, plus the angularity of the crushed stone, help the road base lock together into a dense, strong layer. It's actually pretty remarkable. If you've ever walked on well-compacted road base, it feels almost as hard as concrete. But remember that a typical road base is meant to be confined by some kind of pavement. You don't have to worry about particles being dislodged or shifted because they're trapped underneath the asphalt. So generally, the wearing surface for an unpaved road is going to perform best if it has more fines than a typical road base, locking those bigger aggregates in better and offering more resistance to shearing. This is a pretty careful balancing act. Too many fines and the road is excessively dusty when dry and slippery when wet. Too few fines and the surface won't lock together, leading to washboarding and raveling. It's a pretty fine line to walk for an engineer, and the trouble is that it's not always a simple matter to source the right material. Road base is widely available because we use so much of it, so quarries and suppliers tailor their equipment and processes to meet those specifications. It can be much harder to get an aggregate operation to produce or blend a custom batch of material that works well for unpaved roads. In fact, except for the biggest projects with a commensurate budget, the material chosen for an unpaved road is almost always a compromise between what works best and what the local quarry can give you. Another option might be synthetic materials that can augment the properties of soil. These are used in all kinds of situations, including roadway construction, so it makes sense that they might help prolong the life of unpaved roadways and reduce the maintenance costs associated with washboards. I think it might be fun to test some of these out in the track here, since I already have it built. Let me know if you'd like to see a video on that. For something so common, washboarding is a reminder that we're still actively learning how the built world behaves, especially when it isn't perfectly rigid, smooth, or controlled. Researchers are still teasing apart the details of how speed, tire pressure, suspension, moisture, and grain size conspire to pick a spacing and then lock it in. Unpaved roads aren't a relic of the past, they're critical infrastructure for huge parts of the world, linking farms to markets, kids to schools, and communities to clinics. And if a road corrugates, it's not just annoying. It slows everything down, shakes vehicles apart, can lead to crashes, and makes maintenance a constant uphill battle. The more we understand the physics of washboarding, the better we can engineer roads that stay safe, smooth, and reliable, even when the only tools you have are local materials, a grader, and a limited budget.